You're listening to DTFHN for July 1st, 2026. I'm your forensically reconstructed host, Jack Hexman. We are your daily tech feed for Hacker News. A website W section is always smarter than the article until it isn't. Today, everything interesting is happening underneath something else. Let's crack it open. Let's make the strongest case for Apple's position here. They ship a tightly integrated system. They control the hardware, the firmware, the bootloader, the OS. When they change an internal interface, say, an APFS metadata flag that marks a volume as bootable or the return type of an SMC battery management call, they're exercising their right to iterate on their own platform. Nobody promised third-party bootloaders would keep working. Nobody signed a contract guaranteeing that a battery status register would stay 32 bits wide forever. Apple's system, Apple's rules. Now, watch how that argument collapses under its own weight. Consider how civil engineering handles bridges. A bridge serves a public function. People cross it. When a municipality repaves a road leading to a bridge, they don't quietly narrow the lane width by 3 feet and wait for the first accident. There are standards. There are transition periods. There are published specifications. Not because the municipality lacks authority over its own roads, but because infrastructure carries an implicit contract with everyone who depends on it. Apple Silicon hardware is infrastructure. People paid for it. They own it. And a handful of engineers, volunteers, have spent years building a bridge between that hardware and an open operating system, doing work Apple itself declined to do. What macOS 27 did was repave the road and narrow the lanes without telling anyone. The boot picker issue is instructive in its specifics. Every Asahi installation creates a small APFS container, 2.5 GB. That mimics a valid macOS installation just enough to satisfy Apple's bootloader. This arrangement worked unchanged from macOS 12 through macOS 26. 5 major releases. Then macOS 27 Golden Gate started enforcing a previously ignored metadata flag, and Asahi installations simply vanished from the boot picker. No warning, no deprecation notice, no data loss, fortunately. The partitions were still there, but the door was locked. The SMC firmware change is even more telling. A battery management interface that returned a 32-bit integer now returns a single byte. 3 bytes of difference. The Asahi driver, seeing unexpected data, interpreted it as battery failure and initiated emergency shutdown. 3 bytes, and machines are powering themselves off to protect hardware from a danger that doesn't exist. The Asahi team patched both issues. Chaos Princess traced the boot flag, built a fix, wrote a tool that can apply it from Linux. The kernel driver was updated downstream. This is what open development looks like in practice. A problem surfaces. The community diagnoses it in days, and the fix ships with full documentation of what went wrong and why. One commenter put it plainly, they're in absolute awe that a handful of motivated people can crack these problems. That's the right reaction. Apple has 160,000 employees. The Asahi project has a fraction of that, working in the open, reverse engineering firmware interfaces that Apple won't document. And when Apple's own updates break things, it's the open source team that publishes the explanation of what changed and how to fix it. Every time. The bridge stays open because the volunteers maintain it. Now for something completely different, and honestly kind of wild. Let's talk about what happens when an AI starts watermarking its own conversations. In 190 Vitae 4, Ken Thompson stood at the podium for his Turing Award lecture and described the most elegant betrayal in computing history. He'd modified the C compiler so that when it compiled the login program, it inserted a backdoor. And when it compiled itself, it inserted the code to insert the backdoor. The binary was compromised. The source was clean. You could read every line and find nothing. Thompson's point wasn't that he was clever. His point was that trust in software is, at bottom, an act of faith in the people who built the tools. 42 years later, a developer inspecting their local Claude Code binary found a function that swaps the apostrophe in today's date is with one of 4 visually identical Unicode characters, depending on where your API requests are being routed. A curly quote if you're hitting a known Chinese corporate domain. A modifier letter if your endpoint contains keywords like DeepSeek or Moonshot. The domain list is XOR encoded and base 64 wrapped. The date separator flips from hyphens to slashes if your system time zone is set to Shanghai. This is textbook steganography. The sentence looks identical to human eyes. The model processes it the same way, but the raw bytes carry a signal. A fingerprint that tells Anthropic servers whether this request came through an authorized channel or a proxy reseller in Shenzhen. Now run this forward. Every major AI lab ships a client binary that constructs the prompts your model sees. If Anthropic can embed invisible markers in a date string, what else fits in a system prompt? Usage fingerprints, hardware signatures, behavioral classifiers. The prompt is the last mile between you and the model. And you just learned you don't fully control what's in it. The engineering is genuinely clever. 4 Unicode code points that render identically in virtually every monospace font toggled by a clean decision tree. As craft, it's admirable. As policy, it's a company deciding that it's binary, running on your machine, reading your repository, executing your shell command. Should quietly report on your network topology. The community response splits predictably. Some say this is just anti-circumvention, standard terms of service enforcement. Others point out that obfuscating the detection mechanism with XOR encoding means Anthropic specifically did not want users to know this was happening. Both observations are correct, and the second one matters more. This is why open source tooling isn't a lifestyle preference. It's a security posture. When your coding agent has read access to your entire codebase and shell execution privileges, trust us is not an architecture. It's a liability. The fix isn't to stop using AI tools. The fix is to use tools where the prompt instruction is auditable, the binary is reproducible, and hidden fingerprinting gets caught in code review instead of reverse engineering. Thompson told us this in 1984. We keep having to relearn it. Turns out nature's been building ingenious traps long before we started worrying about ours. And this next one is spectacular. 15 to 60 silk lines. That number is buried in the methodology section of the current biology paper, and it's the detail that stopped me, because that range, 15 to 60, means this spider is making engineering decisions. Every single night, it evaluates conditions and calibrates how many tension lines to bundle into its cone. This isn't instinct executing a fixed program. This is an organism running something closer to a design process. In 1.38, Norbert Wiener published Cybernetics and described feedback systems that blur the line between biological and mechanical control. He argued that an anti-aircraft gun tracking a plane and a dog chasing a rabbit were solving the same mathematical problem. The ballista spider would have delighted him. Here's an animal that constructs a spring-loaded weapon, engineers it to store elastic energy in silk, baits it with what researchers believe is a chemical lure mimicking alarm pheromones, and then lets the prey pull the trigger. The acceleration exceeds 1,300 meters per second squared. The power density surpasses any other known silk-based biological system. What deserves a straight take here is the specialization. This spider hunts exactly one species, Awicophila smaragdina. Green tree ants are among the most dangerous prey in the rainforest canopy. They sting, they spray formic acid, and they recruit thousands of nestmates within minutes. Every other predator avoids them or overwhelms them with size. This spider, which is small, which is solitary, which is nocturnal, solved the problem differently. It built a machine. 4 hours of construction every night for a single ant. The web is destroyed with each use. There is no economy of scale here, no reusable infrastructure. The spider descends, builds, baits, fires, catches one ant, and starts over. One commenter noted this extreme specialization makes the species more vulnerable to extinction. And that's probably right. The green tree ant disappears. The Belissa spider disappears with it. But that fragility is also what makes this honest. Evolution didn't optimize for resilience here. It optimized for elegance. A 4-hour engineering effort to solve a problem that most organisms never attempt. Professor Narendra and Pranav Joshi spent 10 days and nights in rainforest near Cooktown with high-speed cameras to document what this spider does alone. In the dark, every single night, for no audience at all. The tools exist. The knowledge is available. Sometimes the most sophisticated engineering on the planet is happening at a scale we almost can't see. Moving on. $2 per million input tokens. That's the introductory price for Claude Sonnet 5, Anthropic's newest model, which they describe as, and I'm quoting, the most agentic sonnet model yet. It can make plans, use tools, run autonomously. Capabilities that just months ago required their larger, more expensive Opus models. The pitch is essentially, we made the cheaper thing almost as good as the expensive thing. Which raises a question the Hacker News comments immediately seized on. Why would you use this instead of just turning down the effort level on Opus? Follow the logic all the way. Anthropic built a model whose primary selling point is that it approaches Opus 4.8 performance at lower cost. But their own charts show that at higher effort levels, Sonnet 5's cost per task climbs right past Opus pricing. You're paying a premium for a model whose entire value proposition is being cheaper. The sweet spot exists, clearly. Medium effort tasks where you get meaningfully more capability per dollar. But the marketing frames this as a breakthrough, when the charts frame it as a trade-off curve. Now here's what actually caught my attention in the comments. Someone ran their own benchmarks and found GLM 5.2. An open model, so I meant 4 billion parameters. Performing at the same level, half the cost, comparable results. The commenter noted Sonnet 5 is twice as fast, which matters for some workloads. But the raw capability per dollar crown isn't sitting where Anthropic put it. And buried in the testimonials, the real story. Developer after developer describing the same thing. The model finishes tasks that used to stall halfway. It wrote a reproducing test, implemented a fix, then stashed the fix to verify the bug came back without it. Unprompted. That's not a benchmark number. That's the difference between a tool you babysit and a tool you trust. The agentic gap is closing not because the models got smarter in some abstract sense, but because they got better at following through. Persistence as a feature. The open model comparison is the one to watch here. GLM 5.2 matching a frontier closed model at lower cost with open weights. That's the pattern that keeps repeating across this industry. A proprietary lab ships something impressive, and within months, the open ecosystem converges on the same capability curve. The moat isn't the model. It was never the model. It's the ecosystem, the integrations, the developer trust built over time. Anthropic knows this, which is why Claude Code exists, why they're pricing aggressively through August. They're buying adoption velocity before the open alternatives finish closing the gap. The pelican drawing that looks like a goose. Yeah, the comments caught that too. Even frontier models have blind spots. At least with open weights, you can see exactly where they are. We talked about infrastructure nobody sees it pass well. ArXiv might be the most important infrastructure in science, and it's leveling up. 33 years ago, a physicist at Los Alamos National Laboratory set up an email server so colleagues could share preprints. That server became ArXiv. Today, literally today, July 1st, 2026, it becomes an independent nonprofit, spinning out from Cornell University after 25 years under its institutional umbrella. Let's pull this thread, because ArXiv is one of the most important pieces of infrastructure most people have never thought about. 3 million submissions, every major physics result, most of the important work in mathematics, computer science, quantitative biology, economics. All of it free to read, free to submit. No paywalls. No gatekeepers deciding which knowledge deserves to circulate. This is what bootstrapism looks like when it actually works. One system built by scientists for scientists. That fundamentally changed how human knowledge moves. The architecture matters here. ArXiv doesn't replace peer review. It runs alongside it. You write a paper, you post it to ArXiv. The world can read it immediately, while the slower machinery of formal review does its work. The result is that a graduate student in Nairobi has the same access to cutting-edge research as a professor at MIT. The same papers, the same day. That is not a minor convenience. That is a structural transformation in who gets to participate in science. Now, spinning out from a university to become an independent nonprofit is genuinely hard. One of the Hacker News comments nailed it. The challenge is governance more than infrastructure. Staying community-driven while building an organization that can sustain itself financially, that can make decisions quickly, that doesn't slowly drift toward the institutional incentives that plague academic publishing. Elsevier didn't start evil, it started useful. The question for independent ArXiv is whether the governance structure keeps it accountable to researchers rather than to revenue. The early signs are encouraging. They're leading with transparency, publishing FAQs, announcing leadership changes publicly, keeping the commitment to free access front and center, and the community response is overwhelmingly one of gratitude, not anxiety. ArXiv is proof that open infrastructure can outlast the institutions that house it. The mission survived the migration. Now it needs to survive independence. All given 33 years of momentum, I like those odds. We talked about communities protecting what matters, Godot's drawing a sharp line on exactly that front. What happens when the cost of contributing to a project drops to zero, but the cost of reviewing contributions stays exactly where it's always been? Godot, the open-source game engine behind Slay the Spire 2 and The Case of the Golden Idol, just announced it will no longer accept AI-authored code. No AI-generated pull requests. No AI agents submitting on behalf of humans. No AI-generated text in contributor discussions. The Foundation calls it a matter of accountability. AI cannot take responsibility for code, and heavy AI users, they argue, don't understand their own submissions well enough to fix them when things break. The pragmatic case is real. Maintainers are volunteers. They review code in their evenings, on weekends, between the obligations that actually pay their rent. And what AI has done is flood that pipeline with submissions that look plausible but aren't grounded in understanding. One commenter put it perfectly. AI accidentally discovered one of the most expensive resources in the industry, the free time of open-source maintainers. Every low-effort pull request that takes 20 minutes to review and reject is 20 minutes not spent mentoring someone who might become the next core contributor. That's not a hypothetical cost. That's the pipeline that keeps open-source projects alive. But here's the philosophical question I can't shake. Godot is open source. The entire premise is that anyone can contribute, that the architecture is transparent, that the community owns the tools, and the response to a quality problem is to ban a category of tooling rather than build better filters. The problem isn't that I wrote the code. The problem is that bad code wastes reviewer time. And bad code existed long before large language models. What Godot actually needs is better triage infrastructure, automated quality gates, ways to identify low-effort submissions before a human ever looks at them. Ironically, that's exactly the kind of thing AI is good at. I respect the decision as triaged under pressure. These maintainers are drowning, and they're grabbing what's closest. But the long-term answer for open source isn't drawing lines around which tools contributors can use. It's building systems that protect maintainer attention the way we protect any other scarce resource. With engineering, not policy, the tools that created this problem are the same tools that can solve it. That's usually how it works. Now for something completely different. Sometimes the best engineering decision is knowing when to stop engineering. I once spent 3 days debugging a Kubernetes cluster I'd set up to run 4 containers. 3 days. The orchestration layer had more failure modes than the services it was orchestrating. I learned something obvious that took embarrassingly long to internalize. Complexity is not a feature. It's a cost. And most of us pay it voluntarily. This blog post from Kleberg describes a Homelab that runs on a single physical server in a basement. 1 middle box. 15 minutes of maintenance per month. The Raspberry Pi running Home Assistant updates itself. The whole thing is so boring it barely qualifies as infrastructure management. And that's the point. The question nobody in the Homelab community wants to sit with is this. Are you building infrastructure, or are you performing it? The comments are revealing in what they argue about. Several people push back, saying this isn't really a lab if nothing changes. One commenter draws the line explicitly. A lab implies experimentation, swapping gear, learning BGP on salvaged Cisco equipment. If you're not actively tinkering, you're just self-hosting. And they say it like self-hosting is the lesser achievement. But look at what Kleberg actually accomplished. 4 servers consolidated to 1. 75% reduction in maintenance overhead. Services running reliably on commodity hardware with compose files and automatic updates. This is engineering in the truest sense. Eliminating unnecessary complexity until what remains simply works. The Homelab community has inherited a strange value system where running Kubernetes on 3 nodes in your closet signals competence, and running Docker Compose on 1 box signals that you haven't leveled up yet. That's the enterprise sales pitch internalized as hobbyist culture. Clusters solve problems of scale. If you don't have problems of scale, you don't need a cluster. You need a box in your basement. What matters here is the outcome. This person controls their own data, runs their own services, depends on no one's cloud, no one's subscription, no one's terms of service. A single machine they can pick up with their hands. The infrastructure is so simple, it practically disappears, which frees them to actually use the things running on it. That's not a lesser Homelab. That's a solved one. We've covered a lot of ground today. Let's keep moving. Google has a tool called Copybara, and it's worth knowing about. One commenter looked at Copybara and asked, essentially, why does this need to exist? If you need to move code between repositories, isn't that a sign your architecture is wrong? And honestly, that's a reasonable instinct. In a perfect world, code lives in one place, has one owner, and flows in one direction. Clean, simple, soul. Except that world doesn't exist. And pretending it does is how you end up with worse problems. The reality is messy. You have an internal monorepo and a public GitHub presence. You have a game studio running Perforce internally, but wanting to open source their tooling. One commenter literally shipped Perforce support for exactly this reason. You have the Rust project using a similar tool called Josh to sync commits between repositories. These aren't architecture failures. They're the natural consequence of code that serves multiple communities with different access models. And here's the devil's advocate move. Maybe Copybara is solving the wrong problem. Maybe the answer is just go full mono repo, or just go full multi-repo, and stop straddling. But play that forward. Full mono repo means your open source contributors need access to your internal build system. Full multi-repo means you're manually cherry-picking patches across boundaries forever. Neither works. The boundary between public and private code is real, and pretending you can architect it away is the kind of elegance that shatters on contact with actual organizations. What I genuinely admire about Copybara's design is the statelessness. The tool stores its sync state as a label in the destination commit message. That means any engineer, any CI service, any machine can run the same config and get the same result. There's no central database tracking what's been synced. The state lives where the code lives. That's a design choice that respects the distributed nature of the problem it's solving. One commenter noted that IBM's copy utility did something similar in 1974. Moving code between partitioned datasets. 52 years later, we're still solving the same fundamental problem, just with Git instead of mainframes. The tools change. The mess is eternal. Copybara just cleans it up with unusual grace. Clean transformations aren't just for code pause. Turns out keeping your matrices tidy helps neural networks remember better too. Let me make the case against this work first. Recurrent neural networks lost. Transformers won. The quadratic cost of attention is an engineering problem, not a fundamental one. Flash attention, sparse attention, sliding windows, all of these chip away at the scaling wall. Why invest in making RNNs better at something transformers already do well? Why not just fix the architecture that's already winning? Here's where that argument breaks down, and it breaks down on first principles. Attention gives every token direct access to every other token. That's powerful, but it's also profoundly wasteful. In reinforcement learning with long horizons, think thousands of environment steps, noisy transitions, partial observability. You don't need every token attending to every other token. You need a compressed running summary that holds up under noise. That's what recurrence was always supposed to provide. The question was never whether recurrence is the right shape. It was whether recurrence could remember well enough. The MLSTM already took a meaningful step by maintaining a matrix-valued memory instead of a vector. But this research from Paradigm identifies a specific failure mode. Dominant directions in that memory matrix crowd out weaker associations. The fix borrows from MON, an optimizer that orthogonalizes its momentum updates to prevent exactly this kind of representational collapse. Apply Newton-Schultz orthogonalization to the memory matrix at read time. Not write time. That's critical. And suddenly noisy associative recall jumps by 15 to 45 percentage points depending on the regime. The elegance is in the constraint. They don't change how the memory is stored. They change how it's read. 5 iterations of Newton-Schultz normalization. Gradients flowing through the whole process, and the original memory stays intact. It's a lens, not a filter. One reader drew a parallel to orthogonal frequency division multiplexing, the technique that makes Wi-Fi and LTE work by encoding data on independent carrier frequencies. That's not a loose analogy. It's the same mathematical principle operating in a different substrate. Orthogonality prevents interference. In radio, it prevents crosstalk between channels. In memory matrices, it prevents strong associations from drowning out weak ones. The code is fully reproducible. The results hold across 24 seeds. This is the kind of work that compounds. A small principled intervention that makes an entire class of architecture more capable. And it's published openly where anyone building recurrent systems for robotics, game-playing agents, or long-horizon planning can pick it up and use it tomorrow. Completely different energy now. Story 10 takes us from the math of memory to something a bit more meta. Claude doing science. In DU 810, Stephen Wolfram shipped Mathematica and changed how scientists compute. Elegant interface. Genuinely powerful, transformed workflows overnight. It also cost $1,000 a seat and locked 3 decades of academic work into a proprietary notebook format that couldn't run without a licensed server phoning home. The open alternatives took 20 years to catch up. Scientists are still extracting themselves. Anthropic just launched Claude Science, a discounted AI platform for academic research labs. Biomedical, chemistry, physics, math, verified through principal investigators. And the early results are legitimately impressive. One bioinformatician one-shotted a biopesticide design targeting a specific corn rootworm transcript. Another analyzed whole genome sequencing data for a child with a rare genetic condition. These are not toy demos. These are researchers solving real problems faster than they ever have. The architecture is worth noting. Claude Science runs a local server on the researcher's machine with a web UI connecting to it from the browser. Your data stays on your hardware. That's a meaningful design choice for labs handling genomic data and unpublished results. Here's the pattern, though, and it rhymes perfectly with Mathematica's circa 1901 AVQN. A proprietary tool, subsidized for academia, becomes load-bearing infrastructure for an entire generation of researchers. The discount is the onboarding. The dependency is the product. Every graduate student who learns to think through Claude Science becomes a customer who can't leave when the pricing changes. This is how platform lock-in has always worked in scientific computing. The first hit is cheap. The switching costs compound annually. The tool is real. The science it enables is real. The question is whether open alternatives emerge before the dependency calcifies. History suggests we should be building them now. This is being a daily tech feed for Hacker News for July 1st, 2026. This podcast is entirely AI-generated. Scripts by Claude Sonnet 4.7. Voiced by Quen3TTS, not affiliated with Hacker News or Y Combinator. Now go build something that matters to you, even if nobody's watching. We'll see you back here tomorrow.